All right, so we are going to learn about logarithms and the logarithm function. Okay, this is something that's new to us. But if you've ever looked at your calculator and saw the button LOG, log, and wondered what it's for, we're going to find out what it's for today. Okay, this is it's an inverse of an exponential. Okay. Inverse functions, you just switch the x and the y values and you have the inverse function. Or if you want to look at it graphically, an inverse function is reflected across the y equals x line. So if this is your exponential function, that would be a decay one, right? If that were your exponential function, the inverse of that would be reflected across. Okay, so see how they're reflected. And it works both ways. So you could also have the growth. So there's the growth function, and then if you take a look at the y equals x line, and you look at it reflected across, those would be inverses of each other. There's reflected across. Okay? So they're inverses of each other. So mathematically or algebraically, what you would look at is if this is our exponential function, y equals b to the x, to get the inverse algebraically, you flip around the x and the y. So x equals b to the y would be the inverse of y equals b to the x. And now typically we write equations as y equals, okay, instead of x equals. So we need a way how to write this inverse function in terms of y. And that's where the logarithm is going to help us out. X equals b to the y can be rewritten as y equals log base b of x. So those two are equivalent to one another. Couple things that we want to notice about this. Base number is the one being raised to the exponent here. Logarithms also have a base number. Okay? So b and b, these are both the base numbers, and they're staying the same. Okay? And then b to the y here, our base number is raised to the y, what we're equal to on the other side. So what we're going to try to do is, knowing that these two are equivalent to one another, we're going to rewrite the logarithm as an exponent. And then we're going to also have an exponent function and rewrite it as a log. So we're going to try to flip-flop back and forth between these two algebraically. So if we have log base 3 of 9 is equal to 2. First thing we want to figure out is what's the base number?
9 or 3?
The 3 is the base number. Okay? So 3 is the base number, so that means we're going to take 3. We're going to raise it to the second power, and it should be equal to 9. Does that make sense? 3 squared, is that 9? Yes, it is. Okay. So your base number raised to whatever you're equal to should be the value that you're taking the logarithm of. So how would you rewrite log base 10 of 1/100th is equal to negative 2? Other way around. 10 is our base number. So 10 to the what power? Yep, 10 to the negative 2 is equal to 1/100th. And that is what it's equal to. So is that okay? Just rewriting. And you can have these two formulas because these are interchangeable with one another to figure out what goes where as well. So now we're going to go in reverse. So I'm going to give you it in exponential form, and we need to write it as a logarithm.
How would you do it if you can give us one word instead of fraction?
It doesn't matter if it's a fraction. Okay, so here's our exponential, and we want to rewrite it like a log. Okay, so we're going to start off with log, and then what should the base number be? What's our base number? 5. So we're going to put a little 5 below. Yep, log base 5 of 125 is equal to 3. And then the way to just check it, when you add a logarithm and you're going to the exponents, just your base number gets raised to whatever you're equal to. So 5 to the third is 125, and that is what we started with. Okay, so let's try to rewrite the next one. 27 to the 1/3 is equal to 3. Okay, so our log base 27 of 3 is equal to 1/3. Yep, and 27 to the 1/3, and that is what we started off with. Okay, so that's just going back and forth. Being able to go back and forth is going to help us be able to figure out what these logarithms should actually be equal to help us evaluate them and get some actual numbers for them when we simplify them down. So that's what we're going to do next. We're going to evaluate. So we want to figure out what this should be equal to. Okay? And so to do that, we're going to think about this as an exponent. So I have log base 3 of 243. So we're going to think about this as an exponent. What's our base number here? 3. So we want to think 3 to the what power would give you 243? 3 to the what power? To the 5th? Yep, 3 to the 5th. So this is equal to 5. Yep, it's a knowing your exponents type of thing. So if you know your exponents really well, this will go quickly. If you do not know your exponents that well, you will be doing a lot of guessing and checking to figure out what it is. Okay, log base 9 of 9 squared. So what's our base number? 9. So we want to think 9 to the what power would give you 9 squared? Yeah, 2. That one was a pretty easy one, right? It was spelled out for you. Seven looks really complicated, but it's actually not. Ooh. I want to make sure I'm writing that the right way. So this is what we had up there for our functions and how they go back and forth. So if I have 7 to the log base 7 of x minus 1, this has a combination of exponents and of logarithms. But right now the main number here is that 7, which is an exponent. So we're going to try to rewrite this as a log. Okay? So if I try to rewrite this as a log right now, I would have log base 7 of something, that's what we want to find out what it is equal to the exponent, log base 7 of x squared minus 1. Okay, so we just took that idea and we just rewrote it. What would that something have to be? Yeah, x squared minus 1. That something would have to be just that x squared minus 1. They'd have to be the same to get it. So this is just x squared minus 1.
How come like the 7 out in front just disappeared?
The 7 out in front didn't disappear. We were rewriting it as a terms of log. So the 7 is your base number, so we rewrote it as log base 7. Of what? We don't know. We're trying to find out. So of something should be equal to our exponent. So our log base 7 of x squared minus 1. So it didn't disappear. It went right there for our base number for our log. That was in our exponent, though. That's for the other side. This exponent here is our y. Exponent here is our y. That's what it's equal to, so that's where we put it. Now, do you notice anything about 6 and 7? They both had some exponents in there. So do you notice anything about the base numbers? Like here it's a base of 9, and this 9 is also a base. The same. How about for 7? They're both the same. So when those base numbers are the same, what are you noticing about the ultimate exponent then? It's in the answer, right? So here, log base 9 of 9 squared just ends up being 2. That was our ultimate exponent. 7 to the log base 7 of x squared minus 1 ended up just being x squared minus 1. That will happen every time. Okay?
Why did they write 7 out front just to make it more confusing?
This 7? No, it wasn't so it was more confusing. It was written as an exponent first.
Okay.
So we were rewriting it as in terms of log to figure out what it would have to be. Okay. All right, number 8, log base 2 of 64. So what do we want to think of to figure out what this should equal? Yeah, 2 to the what power would give you 64? Yeah, 2 to the 6th power. Okay. Is that all right? Okay, so then we're going to solve these. So to solve these, what we're going to do is we are going to think of how we rewrite these in terms of our exponents. Okay? And we're just going to set up our exponent equation and solve it. So log base 8 of n is equal to 4/3. So how would I rewrite this as an exponent? What's the base number?
8.
8. And what should we raise 8 to?
8 to the 4th.
Yep. So we'd go 8 to the 4/3 should equal n. And now we just have to figure out what 8 to the 4/3 is. Okay, so this brings us back to when we had rational exponents. So the top number is what we raise it to. The bottom number is the root that we take it of. So this is saying the cubed root of 8 raised to the 4th power. Well, what's the cubed root of 8? 2. And 2 to the 4th is 16. So 16 is our n. All right, so let's look at number 10. Log base 6 of x is greater than 3. So how can we rewrite this in terms of exponents?
6 to the 3rd is greater than that.
Yep, exactly. 6 to the 3rd is greater than x. Well, what's 6 to the 3rd?
216.
So 216 is greater than x. We normally write this so that x comes first. So we just say x is less than 216. Is that okay? All right. These look hard, they're not. Log base 4 of x squared is equal to log base 4 of 4x minus 3. Now here we have an equation where we have a logarithm on both sides. Okay. If we have a logarithm on both sides, what do you think our equation could be for this first one, for how we could find our x?
Subtract like the log thingy over.
No, we don't have to subtract the log.
Just do x squared equals 4x.
Yeah, we just do x squared equals 4x minus 3. We can say that because both of those values are inside of your log base 4. So if you take the same function of them, then whatever you're taking the function of them must be equal to each other. And how would we solve this?
Do we ever have ones where they're not the
Factor
same?
it.
No.
Okay.
Yeah, factor it. So we got to get it equal to 0. So x squared minus 4x plus 3 is 0. Because we had to get it equal to 0. So what would we get when we factor this here?
Negative x squared. Well, x negative 3.
Yep, x minus 3, x minus 1 is 0. So what are your two values for x? 3 and 1. Now one thing that we have to take note of is when we had our exponential functions, our graphs, our exponential functions were always greater than 0 for our y's, right? But now the logarithm is the inverse of it. Okay? So if our exponential functions were always greater than 0, the logarithms are the inverse. So for a logarithm, whatever you're taking the logarithm of, it has to be greater than 0 for it to exist. Because we're looking at the inverse of it. So we don't think about y's, we think about the x's. So when we get our values for x here, we do want to make sure that we would still have values that are greater than 0. And I think we do this time. If we plug 3 and 1 back in, we have values that are greater than 0, so they both end up working for us. But we have to end up getting values that would make these positive. Okay. All right, one last problem, number 12. Log base 7 of 2x plus 8 is greater than log base 7 of x plus 5. So what could be our equation here? 2x plus 8 is greater than x plus 5. That 5 looks very strange. There we go. Then how would we solve this? Subtract the x and subtract the 8. So we have x is greater than what? 5 minus 8 is negative 3. If you think about putting negative 3 into both of those, 2 times negative 3 is negative 6 plus 8, so that's a positive number. Negative 3 plus 5, that's also a positive number, so we're fine. So there's our solution. Is this okay? All right.